For many centuries, people believed that the Earth was the center of the universe and that the sun, the moon, the stars, and the planets revolved around it. This geocentric model was supported by the teachings of philosophers and religious authorities. It felt like an obvious truth to everyone at the time because from the ground, it really does seem like the sun and stars move around us. In 1543, a Polish astronomer named Nicolaus Copernicus published a book called On the Revolutions of the Heavenly Spheres. In this work, he proposed a bold and revolutionary idea. What if the sun, not the Earth, was at the center of the solar system? He suggested that the Earth and the other planets orbited the sun. This heliocentric theory was shocking because it went against centuries of accepted wisdom and deeply held religious views. Many scholars and the general public rejected it at first. They could not imagine that Earth was not the center of everything, and some even considered the idea dangerous, resulting in many people even being imprisoned, tortured, or killed if they tried spreading this belief. Evidence gradually built in favor of Copernicus's theory. Johannes Kepler, decades later, refined the model by showing that planets move in elliptical orbits, not perfect circles. Galileo Galilei used the newly invented telescope to observe moons orbiting Jupiter, providing direct proof that not everything revolves around the Earth. Observations of Venus's phases and other celestial phenomena further confirmed the heliocentric system. By the late 17th century, most scientists accepted that the Earth moves around the sun. Hundreds of millions of years ago, all of the continents we know today were once joined together in a single massive landmass. This idea, once considered crazy, eventually became a cornerstone of modern geology. The first serious proposal came from German scientist Alfred Wegener in 1912. He suggested that continents are not fixed, but slowly move across the surface of the Earth. He pointed out that continents like Africa and South America fit together almost like puzzle pieces. He also noticed that the same fossils and rock formations appear on continents that are now thousands of miles apart. He called this supercontinent Pangaea. At the time, scientists rejected Wegener's idea. The main reason was that he could not explain how continents could move. No known forces or processes could push entire landmasses across the Earth's crust. Because of this lack of a mechanism, continental drift was dismissed as speculation. Many geologists believed the continents were rigid and unchanging. Everything changed in the 1960s when scientists discovered more about the Earth's crust and the ocean floor. They found that the ocean floor spreads at mid-ocean ridges and that magnetic patterns in rocks record reversals of Earth's magnetic field. These discoveries led to the modern theory of plate tectonics, which explains how continents move. Most people grow up thinking time moves in one steady flow. You look at a clock, it ticks second by second, and you assume everyone around the world experiences that same rhythm. That idea feels natural because it matches our daily lives. But in 1905, Albert Einstein introduced a theory that completely changed this picture. He said time does not move the same for everyone. Instead, it can speed up or slow down depending on how fast someone is moving or how strong the pull of gravity is around them. This idea became known as the theory of relativity, and it shocked many scientists of that generation. Einstein reached this idea while studying how light moves. He realized that the speed of light stays the same no matter how fast a person or object is traveling. If that is true, then space and time cannot be fixed. They must stretch or shrink so that the speed of light always remains constant. This led him to the conclusion that time itself is flexible. It can bend with motion and gravity, almost like a fabric. At first, many people thought this was nonsense. They argued that our daily experience showed no sign of changing time. You do not feel faster when you sit still, but the truth is that the changes are very small at normal speeds and only become noticeable when objects move extremely fast or when they sit in very strong gravity. Over time, scientists found ways to test Einstein's claims. One important test involved atomic clocks that were flown around the world on airplanes. When the clocks returned, they showed tiny differences compared to clocks left on the ground. The results matched Einstein's predictions. Later, scientists observed time moving differently near very strong gravity in outer space. Modern satellites and GPS systems also rely on time correction because their clocks run slightly faster than clocks on Earth. What once seemed like an impossible idea slowly became accepted as real once the evidence grew. Today, relativity forms part of the foundation of modern physics and technology. For a long time, people believed the universe was quiet and unchanging. Many scientists thought the universe had always existed in the same state and would remain that way forever. This belief felt safe and logical because nothing in our daily lives suggests that space itself could stretch. That changed in the early 20th century, when a few researchers began to explore strange solutions to the equations that describe gravity. One of the first breakthroughs came from a Russian mathematician named Alexander Friedmann. In the early 1920s, he used Einstein's equations of gravity and found that the universe did not have to be static. It could expand or shrink over time. Around the same period, a Belgian priest and scientist named Georges Lemaitre proposed that distant galaxies were moving away from us, meaning the universe was actually growing. His idea suggested that everything had once been close together and that the universe had a beginning. Many people rejected this at first, but then Edwin Hubble made a discovery that changed everything. In 1929, he measured the light from faraway galaxies. He noticed that their light appeared more red, which meant the galaxies were moving away from Earth. He also found that farther galaxies moved away faster. This pattern made sense only if space itself was stretching like a growing balloon. Even with this evidence, some people remained unsure. Strong confirmation finally came in 1965 when two researchers, Arno Penzias and Robert Wilson, detected a faint glow coming from every direction in the sky. This glow matched predictions for leftover heat from the early universe. It showed that the universe had once been much hotter and smaller, then expanded over billions of years into the vast space we see today. Long before modern technology existed, people whispered about governments watching citizens. Most dismissed these ideas as rumors because they sound dramatic and unlikely. Large-scale monitoring of entire populations seemed impossible. That changed as communication systems evolved and new tools appeared. During major wars, including the First and Second World Wars, governments began intercepting messages sent through telegraphs and radio systems. They claimed it helped protect national security. Later, during the Cold War, intelligence agencies in several countries built secret programs to monitor telephone calls and international cables. A few scandals exposed bits and pieces of this activity, but most people still assume governments only targeted criminals or foreign spies. This belief began to fall apart in the 21st century. In 2013, former intelligence contractor Edward Snowden released a huge collection of documents showing that digital surveillance was far broader than the public knew. The documents revealed that agencies collected internet data, phone records, emails, text messages, and other forms of communication from millions of ordinary people. Many of these systems operated through cooperation between multiple countries. Some companies were legally forced to share data, others unknowingly had their systems tapped. Before these leaks, most people would have laughed at the idea that governments stored data about everyday citizens on such a massive scale. But once the documents became public, the world reacted sharply. Courts, activists, journalists, and citizens began demanding answers. Some countries changed laws to limit surveillance. Others expanded oversight to reduce the risk of abuse. Yet, many programs continue to operate in new forms because governments argued that they were important for preventing attacks or tracking dangerous groups. This idea was once viewed as too extreme to believe, and many thought it was just a crazy conspiracy theory. But once the proof came out, it is now something most people believe and just accept. During the Cold War, the United States Central Intelligence Agency carried out covert operations to remove or influence foreign governments. These actions were motivated by fears of Soviet influence, the protection of economic interest, and the desire to maintain strategic advantages. One of the best-known cases is the 1953 operation in Iran. The CIA supported opposition groups, organized protests, and coordinated with local security forces to remove Prime Minister Mohammad Mossadegh and restore the Shah of Iran to power. This operation aimed to prevent Iran from leaning toward the Soviet Union and to secure Western oil interests. In 1954, the CIA also intervened in Guatemala. The agency supported a small rebel force, ran propaganda campaigns, and pressured the government led by Jacobo Arbenz. Arbenz had introduced land reforms that threatened foreign corporate holdings. The CIA-backed efforts ultimately led to Arbenz being removed and replaced by a military government. This intervention contributed to decades of instability and civil conflict in Guatemala. Another notable example occurred in Chile during the early 1970s. The CIA provided funding and logistical support to opposition groups in an effort to destabilize the government of Salvador Allende before the 1973 coup that overthrew him. While many details remain classified, government reports and historical studies have provided clear evidence of the CIA's involvement in regime change. These actions shaped national trajectories, affected countless lives, and raised important ethical and political questions. In the 1930s, astronomers began noticing a puzzling problem. Galaxies were moving in ways that could not be explained by the visible stars and gas alone. Fritz Zwicky, a Swiss astronomer, studied the Coma cluster and found that the galaxies were moving too quickly to be held together by the gravity of visible matter. He proposed that there must be some unseen mass, which he called dark matter. At the time, the idea was largely ignored because it was difficult to test and required the existence of an entirely new type of matter. The theory gained much stronger support in the 1970s when Vera Rubin measured the rotation speeds of stars in spiral galaxies. She discovered that stars far from the center were moving faster than expected. This suggested that each galaxy contained far more mass than could be seen. Additional evidence came from gravitational lensing, where light bends around massive clusters, and from observations of the cosmic microwave background. Together, these observations show that ordinary atoms make up only a small fraction of the universe's matter. Most of it is invisible, exerting gravity without emitting light. Physicists continue to search for direct detection of dark matter particles. While direct proof remains elusive, the accumulated astronomical evidence confirms that dark matter exists, influencing the motion of galaxies and shaping the universe on the largest scales. For much of the 20th century, scientists believed that the adult human brain was mostly fixed. Early neuroscience held that once the brain developed in childhood, it remained stable. This view suggested that brain damage caused permanent deficits, and that learning in adulthood had limited impact on brain structure. Research over time challenged this belief, introducing the concept of neuroplasticity, which is the brain's ability to reorganize itself in response to experience, learning, or injury. Theoretical roots of neuroplasticity trace back to the 1940s, when psychologist Donald Hebb proposed that repeated activity strengthens connections between neurons. Experimental studies later demonstrated structural changes in animal brains. For example, animals that learned new tasks or lost sensory input showed measurable brain reorganization. In humans, research on London taxi drivers revealed that years of navigation experience led to growth in the hippocampus. Rehabilitation studies also showed that training after stroke or injury could help patients recover lost abilities by using alternative neural circuits. Neuroplasticity was initially met with skepticism because the brain appeared stable and delicate. Today, it is a central concept in neuroscience. The concept of black holes started in the 18th century when scientists imagined that some stars could be so dense that their gravity would trap light. At the time, this seemed impossible because light was understood differently, and the idea felt purely theoretical. In 1916, Albert Einstein's theory of general relativity suggested that a massive star collapsing under its own gravity could create a singularity, a point in space where gravity is so strong that nothing can escape. Most scientists consider this a mathematical curiosity rather than a real phenomenon. This view changed in the 1960s and 70s. Observations revealed unusual X-ray sources, which appear to orbit invisible objects with huge mass. Astronomers concluded that these were likely black holes. Later studies confirmed the existence of supermassive black holes at the centers of galaxies. The evidence became undeniable when gravitational waves from merging black holes were detected in 2015, exactly as predicted by relativity. In 2019, astronomers captured the first image of a black hole shadow in galaxy M87. The glowing ring around the dark center matched predictions and provided visual proof. Black holes went from a wild, almost unbelievable idea to a confirmed reality. Today, they play a crucial role in understanding how stars die, galaxies evolve, and gravity shapes the universe. The idea that the universe began in a single explosive moment wasn't always a widely believed concept. When this theory first emerged, many scientists considered it far-fetched and unscientific. The roots of this theory go back to the 1920s, when Belgian physicist Georges Lemaitre proposed what he called the primeval atom, or cosmic egg. When he was arguing that the universe was expanding, he also claimed it might have started from a single, incredibly dense point. When Lemaitre published this, the reaction ranged from skeptical to dismissive. Einstein himself reportedly said, "Your calculations are correct, but your physics is atrocious." In 1929, when Edwin Hubble provided evidence that the galaxies were indeed moving away from us, many accepted this idea that the universe does move, but the idea that the universe began with an explosion-like event was still far-fetched for most. Through the 1930s and 40s, the Big Bang idea remained controversial. Acceptance began shifting in the 1950s and early 60s, when observations showed that distant, and therefore ancient galaxies, looked different from modern ones, contradicting the idea of an unchanging universe. But the turning point came in 1965, when the cosmic microwave background radiation was discovered, a faint glow of leftover heat from the early universe. Over the next decades, increasingly precise measurements showed the cosmic microwave background had the exact temperature fluctuations the Big Bang model predicted. By the late 20th century, the Big Bang evolved from a controversial idea to the overwhelming scientific consensus. Additional evidence, including the abundances of light elements and the measured expansion rate of the universe, perfectly match Big Bang predictions. The idea that human activity could warm Earth dates back to the 19th century, when scientists like John Tyndall and Svante Arrhenius discovered that carbon dioxide and other gases trap heat in the atmosphere. At the time, many people thought the climate was too complex to be influenced by humans, and the notion seemed extreme. By the mid-20th century, researchers began measuring rising CO2 levels in the atmosphere and developing models to predict future climate changes. These early climate models indicated that continued emissions from burning coal, oil, and gas could significantly raise global temperatures, change weather patterns, and melt ice caps. Despite the warnings, many governments and industries ignored them, arguing that climate naturally fluctuated over time. By the 1980s, however, observable changes such as rising sea levels, more intense storms, and shifting ecosystems align with these predictions, making it increasingly difficult to deny the impact of human activity. Today, global warming is widely accepted as a real and urgent phenomenon. It is reshaping the planet in dramatic ways, affecting water availability, agriculture, biodiversity, human health, and natural ecosystems. Scientists now understand that even small increases in global temperature can trigger cascading effects, including more extreme weather events, wildfires, droughts, and the melting of glaciers. Despite decades of evidence, political and social resistance still slows progress. Many people underestimate the long-term consequences, but scientific consensus makes it clear that climate change is one of the greatest challenges humanity has ever faced. Efforts to transition to renewable energy, reduce emissions, and adapt to changes are now critical for preserving the planet for future generations. Viruses were long thought to emerge only through natural processes. In the early 20th century, scientists began uncovering their genetic code, understanding how they infect cells and reproduce. By the 1970s and 80s, advances in molecular biology and genetic engineering made it possible to manipulate viral genomes in laboratories. At first, many considered this idea far-fetched and just science fiction. Early experiments demonstrated that viruses could be altered to study disease mechanisms, develop vaccines, or in some cases, increase lethality. This work revealed how viruses could adapt, jump between species, or change how harmful they are. Today, research into viral engineering is conducted under strict safety and ethical regulations because of the potential for catastrophic outcomes. Labs worldwide now study engineered viruses to understand pandemics, improve treatments, and develop life-saving vaccines. What once seemed impossible is now an essential tool in modern medicine and biotechnology. Thank you very much for watching this video, and if you learned something, make sure to leave a like. Comment down below your thoughts on any of the theories that turned out to be true I discussed in this video, and subscribe if you would like to see a part 2 or more videos like this one. Thank you again, and goodbye.